Hi everyone. Welcome to our 22nd session of the MedAI group exchange sessions. And this week we are very happy to have Jonathan Crabbé from the University of Cambridge, England, here with us to present his research on explainable AI and its applications to time series. Jonathan is currently a PhD student in the Department of Applied Mathematics from the University of Cambridge and supervised by Michaela van der Schaar. His research focuses on the development of methods for explainable artificial intelligence and is particularly interested in understanding the structure of latent representations learned by all our state-of-the-art methods, and especially relevant for time series models and forecasting. So thanks so much, Jonathan, for joining us today. And before we start, do you have any preferences on how you'd like to take questions?
So hello, I'm perfectly happy with people interrupting me to ask their questions.
Awesome. Okay, so let's try to make this session as interactive as possible. And without further ado, let me hand it over to Jonathan.
Okay, thank you very much, Nandita and C, for organizing this. I'm extremely happy to be here with you today. So today I'd like to spend some time to talk about this very exciting research that is done in explainable AI. Without further ado, I'd like to give an outline of this talk. So I will start with an introduction of explainable AI for the spectators that are not entirely familiar with this subject. So if you don't know anything about explainable AI, don't worry, I will really start from scratch in this talk. Then I will focus on a particular family of explanation methods that we call feature importance. I will discuss it in a very general setting, and then I will particularize the discussion to the time series setting, which is our topic of interest today. After discussing existing methods for feature importance in the time series setting, I will present my own method to do this, which is called Dynamask. So that's it for the outline. Now, let us dive in the subject. So let us start with the big picture. In this talk, I will detail what I mean by explainable AI. Then I will tell you why this is important as a research agenda, and at least I think so. So note that for each section, I've put some useful references here below. So if you want to go beyond my talk, and if you want to learn more about the subject, please read these papers. They are very well written and very interesting papers. So our starting point is this blueprint. Believe it or not, but it describes a big portion of machine learning models. In this blueprint, the machine learning model is represented by a black box function f. So you see that this black box function just eats input features and spit out predictions. To make this more concrete, let us consider some examples of typical machine learning models to show how this blueprint is actually reflected in them. So maybe the most popular example in machine learning is image classification. In this case, the input corresponds to the pixel representation of an image. This pixel representation is fed to an image classifier that will spit out a label that represents what's on the image. So in this case, the image represents a dog. So the image classifier hopefully will identify that there is a dog on the picture. So closer to the medical world, we could imagine another example that computes the risk of the mortality of a patient in a given time frame. Here, the input will be a set of biomarkers that describe the state of a patient. Then the model will eat this set of biomarkers, and then make a prediction of the chances of survival for this patient. Finally, let me show you a last example of this blueprint. Here, the input is a set of time series, which represents some quantity that vary over time. So this can be, the temperature over the year, or the price of a stock on the market. So what the black box is doing here is that it's, analyzing this time series to output a prediction. A typical example in the time series setting is, time series forecasting. In this case, you use the past to predict the future. Later, we will focus on this particular time series setting. But for now, I'd like to go back to our generic blueprint. This black box turns this input feature X into a prediction Y. Since machine learning models are black boxes that typically involve millions of non-trivial operations, this is very difficult for us human beings to understand what's happening inside of this black box. So it seems like a complicated task to explain what's happening. So it's natural to ask if it's worth the effort. Well, I think that the answer to this question is absolutely yes. And I'd like to give you 3 reasons to justify this. To contextualize the first motivation, I'd like to note that machine learning models are more and more involved in high-stake domains. Whether it's transport, medicine, or finance, you will see that these models are going to become more widespread and to assist human beings in decisions for these high-stake domains. Here I've included an example from Cambridge, where trials are made with self-driving buses. Of course, this is one example, but you can have many of them. So even though this premise of machine learning models impacting high-stake domain is very exciting, we have to remain cautious with that. Is that we don't want to let these models take important decisions for ourselves without being involved in this process. There is this really nice quote from Rabelais that sounds much better in French, but that reflects well this idea. Science without conscience is but the ruin of the soul. So if you are interested in this risk and all the philosophical questions related to using machine learning models blindly, I can only recommend you this brilliant book from Stuart Russell, Human Compatible. I'm not going to go into details of that today, but rather I just like to follow a more pragmatical approach and ask you, how can we use these models more responsibly? Well, I like to think of a good use of these models as a human expert. If a human expert makes a recommendation to you, you can interact with the expert to make sure that you understand the recommendation that this expert came up with. Of course, in this setup, we have two humans that are using language as an interface to communicate with each other. If you want to do the same with one human and one machine learning model, we need to create this interface. This is where explainable AI plays a role. Creating this interface is one of the purposes of this research direction. Of course, if you want to make explanation module as rich as our human-to-human communication system, much work has to be done, right? Nonetheless, we have a good reason to do explainable AI now. Develop an interface that will empower and not replace the user of machine learning models. Now, let us jump to the second reason to do explainable AI. For this, I'm going to ask you a question of the utmost scientific importance. How do you recognize a tench? Well, one could argue that its tails or fins have particular shape. Another way is through the body that has a distinctive color. Well, you can come up with many solutions to these problems. But now I'm going to ask a more interesting question. How does a state-of-the-art computer vision model recognize a tench? Well, the answer is in this paper from Brundle et al. As you can see here, their model pays attention to some tiny part of the image that look like fingers. You can see here, you have something that looks like fingers. There you have something that looks like fingers as well. And on all of this image, you have fingers. So that's a bit strange because tench don't have fingers, right? So what happened here? Well, you can have a quick answer by just typing tench on Google image. What you will see is that most of the picture involve fishermen that are holding the tench. Of course, this set of images are biased. A tench can perfectly exist on its own without being held by the fingers of a fisherman. The problem is that the computer vision model will typically pick up these biases. And hence, a tench will be identified without actually paying attention to the tench itself. So let us sum up. As we have seen, we collect the data with our own human biases. In some cases, these biases can be very harmful. You could just think of gender or racial biases. Those are things that we definitely want to avoid. The problem is that these models that are trained on top of this data will often pick up these biases. How can we prevent this? Well, as you have seen on the previous slide, explainable AI often allows you to detect the biases that these models picked up. You can then use the information to create a better model and collect better data. So now, for the third motivation, I thought that it was relevant to take this illustration from DeepMind's AlphaFold. As a reminder for the rare people who missed it, this team has constructed an amazing model that predicts the shape of proteins in space. So I think that this example crystallizes well the growing interest for machine learning models in other branches of science. Well, it is not surprising that machine learning models are gaining the interest of all sorts of scientists. These models make predictions that are often more accurate than more traditional approaches. However, every scientist knows that accuracy is not the only thing that matters. Even a model that is infinitely accurate will not be completely satisfying to a scientist. Indeed, science is about understanding, and we know that there is no understanding without explanation. I think that this is well encoded in this Latin proverb that has been popularized by skepticism. What can be asserted without evidence can be dismissed without evidence. Well, the problem is that machine learning models by themselves assert predictions without evidence. Of course, as we've already said, explainable AI aims precisely at understanding these predictions and explaining them. So in a scientific perspective, this understanding that which is precious. So on this slide, I have compiled these 3 reasons that I gave you to do some research in explainable AI. Of course, there are many more reasons to do this, but I think that those are already good starting points. Now, let us go back to our previous blueprint. So we have seen 3 reasons to understand what's happening inside this black box. Now, a natural question to ask is, where shall we put the explanation on this blueprint? Well, one possible approach to do that is to do what we call white box modeling. The idea here is that you replace the black box with a white box, which is an approximation of the black box by a simpler model. This simpler model allows to understand what's happening to the feature to come up with a prediction. So the flow between these 2 steps is actually understandable. Typical example of white boxes are linear models or even decision trees. However, when you see this, you can definitely argue that the knowledge you gain about the white box might not be true for the black box. Indeed, this simple surrogate model that you trained might perfectly oversimplify the black box. Hence, how do you know if you can trust the insights that you have from your white box? This simple reasoning allows us to motivate another approach that we're going to follow now. This other approach is called post-hoc interpretability. Here, you keep the black box intact, you don't touch it. The only thing that you change is that you add a module on top of the black box. This is the explainability module. So this module is aware of the black box as well as the input features. So for each prediction made by the black box, this module will output an explanation. In doing this, you make sure that the explanations you generate are directly connected to the black box and not to an intermediate surrogate model. Now, if you think about the way we provide explanations, it's actually quite insightful, because what your brain typically does is that it solves problems in a black box manner. However, you are able to explain these predictions to another human being by using an interface, which is here language. In some sense, you could consider the explanation module that I showed on the previous slide as a language between machine. At this stage, you might wonder what these explanations look like in practice. Well, to give an illustration, it is useful to take our image classifier. How can we explain that this image classifier recognizes a dog on this picture? Well, the first example of explanation is through feature importance. The idea here is to highlight the parts of the input that motivate the prediction. For instance, a model might pay attention to particular parts of the image to identify a dog. So here, for instance, the nose and the ears. A second approach is given by example-based explanations. These explanations will typically contextualize the prediction by presenting similar examples from the training set. In our case, this might be images of other dogs that the model has previously seen and that resemble the dog that it has to classify at the moment. The third example of explanation is given by rule-based explanation. Here, these methods present a reasoning that might involve abstract concepts. By following the reasoning, you arrive at a prediction. So for instance, if you have an image that has big ears, a wet nose, and some animal that wants snack, then you know that you are observing a dog. Of course, these are just examples, and there are other types of explanations that I'm not covering here. For the rest of the talk, however, I'd like to focus on the first element of this test, so feature importance method. So we have seen a small example of feature importance method on the previous slides. However, I'd like to take a step back to explain why it is genuinely a challenging problem in general. Then I will quickly present the existing approaches to tackle this problem. I'm going to start with a simple problem to illustrate the difficulty of feature importance. Suppose that we have a really easy black box, so not really a black box, but here we are going to treat it as such. So here this black box depends on 2 features, x1 and x2. So as you can see, you obtain the output of the black box by summing 2 functions of the features. So first one is a quadratic function of x1, and the second one is an exponential function of x2. So now I'm going to ask you a very simple question. What is more important for this black box, x1 or x2? Well, you could argue that if x2 is bigger than x1 and both are positive numbers, then x2 is more important because the exponential is much bigger than the quadratic function. However, you could also consider the scenario where both numbers are negative, and in this case, the exponential will be typically 0 or very close to 0. So the quadratic function seems more important. So x1 seems more important. In fact, both of these reasonings are correct, and many more reasonings like this can be done. What this very simple example shows you is that when you deal with nonlinear functions like this, you might be unable to draw global conclusions in terms of feature importance. You might have to solve these problems in a case-by-case fashion. Now here, we have a very simple function of 2 inputs, but I guess that you can imagine that things get much worse when you have more features and when you make these features interact with each other, as it is typically the case in a deep neural network. So this problem indeed seems complicated. How can we solve it? Well, maybe you don't have to solve the full problem. Indeed, you might just be happy to know what features are important for one prediction rather than for all predictions. Hence, you can just compute this feature importance score for a given input. So here I denoted AI of f and x, and this is just the importance of the feature xi for the black box f around x. So here you have a local notion rather than a global notion. So you work at the vicinity of a point inside the input space. So how do we define these importance scores? Well, actually, there are infinitely many ways to do this. Fortunately, you can filter some possibilities by asking these scores to obey some useful properties. So here I've put a simple example of property, completeness. So what completeness tells you is that if I take the sum of the importance scores, then I recover the black box function, the black box prediction up to a baseline. So this might seem a bit abstract now, but I'm going to illustrate this to make it more clear. So here, as you can see, I'm starting from this baseline, which is E of f of x, which is the expected prediction for the black box. So you can see this as the average prediction for the black box. So this is my baseline. Now I'm going to add the contribution of each feature to this baseline. And these are the important scores that you can see here. So some of these important scores are negative, so they are going to drive me away from this, drive me closer to the baseline. When I sum over all of these important scores, I recover the black box prediction, f of x. So in some sense, this property allows you to interpret these important scores as forces that together give you the black box prediction. So if you pile up enough of these properties, you might actually be left with only one definition. A popular example of this is SHAP, which is important score method that is defined by only 4 axioms. So if you fulfill these 4 axioms, then you can only be SHAP. So now I'd like to bring your attention to feature importance in the time series setting. It might appear as a particular case as what we have already done. However, in some sense, it is not, because the reality is more complicated than that. However, before going into all of these details, I'm going to quickly give a motivation to pay attention to this particular restricted setting. The first motivation for focusing on time series models is that time series amount for a big fraction of the available medical data. Whether you talk about electronic health records, survival analysis, disease progression, the dynamic context seems to be a big deal in a medical context. Maybe one reason for this is that time series allow to model an evolution, and in some way, this gives a more detailed story than plain tabular data. Of course, this means that the explanation themselves can take richer forms. If you think about feature importance, for instance, some feature might only be important in a given dynamical context. You can think, for instance, of a patient state that improves quickly just after a treatment. Here, the timing makes a lot of sense. Finally, those of you who have worked with time series data know that it's often very messy. Whether it's variable length of the time sequence or missing data at some time steps, there are a lot of difficulties that occur very often in the time series setting. The very fact that we have these extra difficulties should directly hint us to be even more careful with the resulting models, and hence try to understand what has been learned. And then we need to do explainability, of course. So now that we have some motivation to focus on explaining time series models, I'm going to formalize the problem a bit better. Let us adapt our previous blueprint and make it more specific. We start with this input time series, which represents the variation of some feature over time. So here, I represent the time series as a matrix with the time on the one axis and features on the other axis. So in some sense, this matrix just allows you to track the features over time. We feed this time series to a black box and get a prediction that we would like to understand. In this case, we will explain the prediction of the black box F by highlighting the parts of the time series that are important for this black box. we represent this by a mask that is a matrix of the same shape as the inputs. For convenience, I will normalize the importance scores that are inside this mask. So for instance, if you have a mask coefficient of 0, this indicates that the feature is not important and is represented in red in this picture. This mask coefficient is going to be set to 1, and this is represented in green on this picture. So it seems like a simple problem, and it seems again to be a particular case of feature importance problem. However, I will now show you that the generic feature importance methods don't work well in this method, in this setting. Oh yeah, I forgot to say that, but actually why we call this a mask, because we can just superpose this on top of the time series to see where the important part is. Okay, so let us try to use existing methods on a problem where we know the solution. Well, suppose that I start with a time series and a model for which I know where the important part is. This is represented by this true mask that you can see here. What I can do is to use popular feature importance method on top of this to see if they recover the important part. And if you do that, you will notice that those methods identify too many features as important. And also, they are not very legible. The mask that they produce is not very legible. So you might wonder why. Why is that so difficult? Like, there is nothing very difficult about this problem. Well, one possible answer to this question is that nothing encourages these methods to be parsimonious and highlight no more feature than necessary. If you look closely at the images, you will notice that the truly important features will indeed be highlighted most of the time. But a lot of features that are not important will also be highlighted. So there's nothing that kind of push these methods to be parsimonious. And that's a problem in the time series setting, because you typically have hundreds or even thousands of features that you track over time. Another possible answer is that, these methods miss an important part of the story, because time induces a context. The variation of the feature over time has a particular order. This method that I have presented here, they don't take this order into account. This is probably the reason why they don't work very well in the time series setting. So maybe it is useful to consider a concrete time series to illustrate what I mean by time context, because I'm using this word a lot. So now I'm going to give an example to precisely define what I mean by that. To do this, let's take a toy example of a model that decides to wait, buy, or sell a security by studying its price over time. So as you can see here, this model will decide to wait, and it will decide to recommend me to buy the security, or to sell the security just after a maximum price. And conversely, it will recommend me to buy the security just after a minimum price. So this is a very simple example, but you see here already that to detect a minimum or a maximum price, you need 3 consecutive time steps. And you need these time steps to be consecutive, of course. So time induces a context, and this context matters in this case because the model relies on this context to make the prediction. The problem is that explainability methods that are model agnostic, like SHAP or LIME, they treat each time step as a separate feature, and so they kind of forget about this time ordering. This time context is kind of forgotten. So this motivates another approach that is more specialized to the time series setting. Unfortunately, the literature on this subject is quite sparse. However, there are a couple of methods that do that, and I'm going to cover this in the next slide. So our first stop is retain, which is a particular model architecture that allows to compute the importance scores in a canonical way. So let us look at the architecture of retain. So as you can see here, you start with a time series, and then you are going to linearly embed this time series. Now that you have your embedding, you are going to feed the embedding to 2 recurrent neural network arms that are going to output you its attention scores. So one of the arms is going to give you an attention scalar, and the other one is going to give you an attention vector. You recombine all of this by using an Adamar product. So you can recombine the embedding, the attention vector, and the attention scalar by taking the Adamar product between them. And then you linearly map the result to the output. So this is the retain architecture. So I'm not going to go into details of this architecture, but what's important to notice here is that all of the green arrows on this graph, they represent interpretable operations. So here, for instance, you have a linear map. Here you have another linear map, and here you just have Adamar products. So what this allows you to do is to compute the importance scores as a closed form expression that depends only on this these attention vectors and these attention scalars, and of course of some parameters of the model. But these attention vectors are telling you where the important part is. So this is also, maybe I should just say that here you see that I've changed the notation quite slightly, because here you have two indices for the importance vector. You see that the importance has the time index and the feature index. Before it only had a feature index. So here you need to know what is important and when. So this is why you have two indices. So there is another approach that works for classifier that is called fit. Here the idea is to compute the contribution of each feature to the prediction shift over time. So here you see that the first term in this expression will just describe the full time shift between the prediction made by the model at t-1 and the prediction made by the model at t. And here you see that the second term in this expression computes exactly the same thing, except that you append this feature xti to the prediction at t-1. So you kind of see how this feature completes the prediction at t-1 to get you closer to the prediction at t. So in this way, the importance score is big whenever the second term is small. You can convince yourself that it's the case whenever the feature I contains the relevant information to cancel this time shift between the two time steps. So now I will present Dynamask, which is 21. So I should stress that I'm not the first one to talk about masks. There are two excellent papers from Fong and Vedaldi that have introduced this notion of mask in the computer vision setting. So if you don't know this paper, I really recommend you to read them. These are excellent papers. However, today we are interested in the time series setting. So let us dive in this subject. The premise of our method is that important features are detected by studying the effect of their perturbation on the model's prediction. In particular, important features affect the model's prediction when they are perturbed. To illustrate this, let us take back to our previous recommender system. As you can see here, at the last time step, the model recommends me to sell the security. I'm wondering if the previous time step is actually important for the model to arrive at this conclusion. So what I do is that I perturb this previous time step. And I observe that actually, yes, the prediction changes. So this time step must be important. On the other hand, irrelevant features don't have effect on the model when they are perturbed. As you can see here, perturbing this other time step has absolutely no effect on the prediction. So it's probably irrelevant. So as I've previously said, the information about feature importance is stored in a mask coefficient. Of course, the purpose of this perturbation scheme is actually to identify these mask coefficients. However, before going into that, I'm going to explain first how. So in this paper, we introduced the notion of dynamic perturbations. Those are perturbations that leverage the contents induced by the time series. Let us now give a detailed definition of what I mean by dynamic perturbations. So I should probably emphasize that this definition is going to be a bit abstract first. So we'll then give an example that will make hopefully everything a bit more clear. So our starting point is that the perturbation operator is associated to a mask. So here I denote this perturbation operator pi m, big pi m, and you see that it's tightly associated to this mask m. So you might wonder why. Actually, it's not very surprising, because if you want the mask to identify the important part of the time series, there should be some form of communication between the way you perturb and the mask itself. So this perturbation operator acts on the space of time series, which I represent here as matrices. So these perturbation operators, what I'm going to do is that I'm going to explicit it. The first thing that I'm asking is that the strength of the perturbation operator depends on the mask coefficient. So here you see that the perturbation of the operator, the perturbed version of the time series at time t for feature I, is equal to this pi function, which depends on the time series itself and on the mask coefficient. So I'm not going to take any function, actually. I'm going to restrict the family of functions that I'm using for this. What I'm asking is that these functions should be such that important features are unperturbed. What this means really is that if I set the mask coefficient to 1, which means that the feature is important, then this perturbation operator trivializes. It just returns me the value of the time series at this time step. So now you can just ask yourself, why do we do that? Well, the fact is that the mask is supposed to tell the perturbation operator where to hide the irrelevant features. So that's what I said previously. The mask hides the irrelevant features. However, relevant features should be conserved by the mask. So the information that are contained in relevant features shouldn't be touched by this mask. Now, finally, I'm talking about dynamic perturbation operators. So I should refer, when I'm talking about this, I refer to perturbations that use neighboring time steps. So as you can see here, you have two window parameters, W1, W2. And pretty much what this equation is telling you is that for all the values of the time series that are in a window around this time t that you are perturbing, so you see that the window is created by W1 and W2. So for all of the values of this time series that are inside this window, well, the perturbation use this value of the time series. So they enter the perturbation themselves. So it is a bit weird, and I'm going to explain this a bit better later. But this notion of dynamic perturbation operator is crucial because this is where actually the time context plays a role. You see that this perturb and the feature that you perturb. The way that this perturbation changes is actually induced by the time series itself. So you see here, that's why you have this dependency. This perturbation depends on the value taken by the time series. So hence, in some sense, you can consider that the perturbation is induced by the time series, and so by the time context that is kind of carried by this time series. So I understand that this definition is very abstract. So now let us take a very simple example to make this more concrete. So I'm taking this simple perturbation operator that involves only the input and a moving average. So you see here that I compute this moving average around the time t by using these two windows operator that I have the windows number parameters that I've defined on the previous slides. So maybe let us just visualize what's happening when I'm doing this perturbation. So I'm starting with this time series, and I'm going to focus on a particular time step, t equal t star. So what I'm doing is I'm taking a window around this time step. And in this window, I'm going to compute the average value of the time series. So this is the moving average that I'm not mu. So what this perturbation is doing is that it's going to move the initial point closer to this moving average. The extent to which you are moving this point in this direction is actually measured by this max coefficient, mt star and I. Now, of course, you could change the way you deal with this window. For instance, you could give more weight to points that are closer in time in the way you compute this moving average. So you can use a Gaussian kernel to give more weights to points that are closer to this time step t equal t star. Of course, you can also decide that you can only choose past values of the time series to construct the perturbation. For instance, if you don't know the future value of the time series, which is often the case in time series forecasting, then you can only rely on past values of the time series. So you can have a window that only covers past values of the time series. So I like these simple examples because it illustrates very well how you take this time context into account in the way you build the perturbation. Of course, you can check that I gave you earlier. So as you can see here, setting the mass coefficient to 1 indeed trivializes the perturbation. And you can compute the partial derivative of this perturbation with respect to the values of the time series. And you have something that does not always vanish. So you are good to go. So what I'd like you to understand at this point is that this definition that I gave you previously, it is just a prescription. In principle, you could use any kind of perturbation operators that satisfies this definition and use this perturbation operator to detect important features. So you see here that you have a generic formalism that can perfectly adapt it to specific domains. However, I didn't tell you the most important part of the story. How do we actually get these mask coefficients? And so how do we actually build this mask matrix? Well, at this stage, it is very easy to answer this question. We just have to assemble all the pieces of the puzzle. So we start with this input time series that we feed to a black box to get a prediction. As before, the mask represents the parts of the input time series that are important. We would like to learn this mask. To do that, we use the mask to build the perturbation of the input. So this is where this perturbation operator plays a role. We then feed this perturbed input to the black box, and we get a perturbed output. So as I said previously, the mask should ideally conserve the relevant part of the time series and perturb the rest. So we cannot actually obtain this behavior by making the perturbed and the unperturbed outputs resemble each other. In this way, this mask will conserve the part of the input time series that actually is useful to reproduce this black box prediction f of x, and it will perturb the rest. So we do this by just propagating the error between the two outputs and correct the mask in this way. So this blueprint is the blueprint of Dynamask. Of course, there are some subtleties that are not included in this blueprint, so maybe I should spend some time to explain that. When fitting the mask, we have to pay attention to several things. The first one is that, as we have seen, we have to make sure that the mask selects the relevant information. So this is done by making sure that the perturbed prediction actually resembles the unperturbed prediction. Then we have to make sure that the mask actually selects some features. Indeed, if you have a mask that tells you that all the features are important, this is not very helpful, right? So we achieve this by adding a term to the objective that imposes sparsity on the mask coefficients. Finally, the user might have some prior knowledge or desiderata about the mask itself. For instance, we might want to avoid to have many quick jumps of the saliency over time. So you might avoid, for instance, to have something that is important, not important, important, not important, important, not important. You might want to penalize for, changing your mind all the time. So if it's indeed the case, you can add another term to the objective that encodes this prior knowledge or prior desiderata. So now that we know how to fit masks, I'd like to make an interesting parallel with information theory. If you recall that mask coefficients are between 0 and 1, well, it is tempting to interpret them as probabilities, right? Well, interpret this mask coefficient MTI as the probability that XTI is an important feature for the black box F. So if you do that, actually what you have here is a Bernoulli random variable. You can compute the entropy of this random variable. And you can actually do that not only for this random variable, but for the whole mask. So you do that by summing over all the indices. So over all the time, what you get then is what we call the mask entropy. You can easily check that this entropy is maximal whenever the mask coefficients are all set to 0.5. This corresponds to a mask that indicates that all features have 50% of chances of being important. This is not very insightful, right? Conversely, the entropy is minimal whenever the mask is binary. This corresponds to a mask that indicates that the importance of each feature, it indicates the importance of each feature with certitude. So it will say that this one is important with 100% of probability, and this one is not important with 1. It seems a bit abstract now, so let us take two examples to see what entropy means in practice. First, let us consider a mask with high entropy. As you can see here, this mask contains a big range of mixed scores. So there are green part of the mask, red part of the mask, white part of the mask, and a lot of shades in between. So you can see that this mask is quite difficult to read. And of course, it gets worse if you increase the number of features, which is typically the case for higher dimensional time series. Next, we can consider a mask with low entropy. As you can see here, the mask is almost binary, so it's much easier to read. Hence, entropy seems to be somehow a useful metric to measure how legible the mask is. So I'm not going to go into details for this, but of course, if you are interested. So by putting all of these ingredients together, we can build masks and see how well they recover truly important features in an experimental setting when the ground truth importance is known. In our experiment, we compare the mask obtained with Dynamasks against a set of baselines feature importance methods. So you see in the baselines, for instance, that I consider methods like retain, which are specialized for the time series setting. And I also consider methods like SHAP or LIME that are model agnostic methods and that will work for any type of data. So in doing this experiment, we noticed three things. The first one is that Dynamask offers a better detection of important features. This is reflected by a higher precision and recall when the ground truth importance is known. The second one is that the masks outputted by Dynamask are more parsimonious, which means that they typically select no more features than necessary, or at least not too many features, which is not the case of how other methods that will select a lot of features. The third one is the fact that Dynamask produce more legible masks. So it has to do with this notion of entropy that I described before. So of course, if you want more details on this, I really invite you to read the paper. Everything is in section 3 under supplementary material. So I'd like to end this talk with a look on the future. I think that there are many things that could be improved in the approach that I have described here. Firstly, we know that characterizing the prediction of a model just on the basis of the output, it's a bit reductive, right? Modern models typically involve a lot of latent representations that transform this input into the prediction. So there is a lot of things happening in between the prediction and the input and the output. So it would be nice to look at these latent representations to have a better understanding of these models. Next, feature importance is nice, but it only tells a very tiny part of the story, really. We know what features are important, but we don't really know why. So contextualizing these important features with relevant examples would be a very good way to tell a more insightful story. Finally, it will be interesting to provide explanations that clearly indicate when the model can be trusted and when the model cannot be trusted. So if you are interested in any of these points that I have mentioned here, I really invite you to stay tuned because I'm going to present a walk at NeurIPS 2021, which is called Explaining Latent Representations with a corpus of examples, and that is really motivated by these 3 points here. So I hope you enjoyed the talk. I thank you for your attention. And if you want to learn more about the subject, please check my GitHub or my paper. Thank you very much.
Oh, thanks so much, Jonathan. I think that was a very comprehensive talk and we learned a lot. Before we move on to questions, maybe we can give a round of virtual applause to Jonathan. And now we leave the floor open for questions.
May I ask a question?
Sure.
So do you initialize the mask, or you just random initialize always some like a priori like domain knowledge?
Yeah, it's a very, very good question. So I'm initializing the mask by using this kind of information theory perspective, which means that I'm saying that at the beginning, I don't know if a feature is important or not. So I initialize it at 0.5, like it can be important, it cannot be important. I initialize all the mask coefficients to 0.5. So it's 50-50 at the beginning.
Okay, I see. So so if we have some like prior knowledge about like what might be important, then we could actually like initialize the mask with this.
You can absolutely do that. Yes, yes, yes. It's possible. Like there is a parameter that allows you to choose the initial coefficients of the mask.
I see. And could you go to the slide where you show like the explanations and compare it to different methods? I think
is it
probably the next slide.
This one, yes, perfect.
Yeah, so I noticed that the mask produced by Dynamask, there are some like a few intervals that are completely zero, but it's actually true, or it's like actually quite important in the true saliency. Do you have an explanation for that? Why this is this method produces?
Yeah, absolutely. So this has to do with this notion of parsimony that I have talked about before. Like, like this mask will typically cut. So like you can feed the mask with different areas of the mask. So what I mean by area of the mask is, like the mask is, I can give you a budget I give a budget to the mask and say, you can identify 10 features as important or 20 features as important. And what are the 10 most important ones? If you have to pick 10, which are these, And you can do that with many values and then, select what we call the extremal mask, which is the one that, will select just exactly the minimum number of features such that the error between the two outputs is small enough, So you are able to tolerate an error, and you select the minimum number of features such that the error between the perturbed and the unperturbed outputs is small enough. So this has to do with this notion of parsimony. Here, there are some parts that are missing because the budget of the mask was, capped up, and it couldn't go identify more features. Of course, if you allow the mask to have more budget, then you will identify these other important features in between.
Okay. Thank you.
I have a couple of follow-up questions as well. So
Sure.
In your previous slide, actually, when you talk about the cost that you put on the mask based on prior conditions, I think just the previous slide. Yeah.
Yes.
So the cost that you put for making the masks legible, instead of having this, could you also use the entropy condition? Like you want to minimize entropy as the condition here in order to make your masks more legible instead of having a window or saying that they should be parsimonious?
Absolutely. So that's a very good question. So you could definitely regularize this by adding the entropy. The reason why I'm using this term here, actually, it is not very well defined on these slides, but actually you have this parameter A that you see here, which is the area of the mask. So this has to do, with the budget that the mask has that I was talking about just before.
I see.
So you can actually change this parameter, and you can try different budgets and see where the mask actually, when you can just plot the error between the perturbed and the unperturbed output as a function of this budget A, and see where increasing A more doesn't reduce this error between the perturbed and the unperturbed output. So this is why I prefer this regularizer. However, if you don't know anything about if you don't want to do this budget analysis and you want to allow your mask to select what it wants really, I think that the entropy is a good regularizer as well. But if you think about this, this kind of does the same thing, because this will typically encourage the mask coefficients to be close to 0 and 1. And this is the case where the entropy is maximal, right? So you kind of minimize the entropy as well by using this regularization here. The only difference is that it allows you to set a budget.
I was thinking that if you do not have a very strong parsimony condition on your inputs, like let's say your time series can very widely vary, then your entropy will automatically take care of it without you needing to put a regularizer that puts that condition.
Absolutely, absolutely. So if you don't want to think about this at all, I think that the entropy is actually a good regularizer.
And just another follow-up question. If you go back to your full framework where you put all the pieces of the puzzle together.
Yes.
So in this case, where is the extent of the perturbation actually coming from? Like, what's the scale of the perturbation? Like, which part of the equation corresponds to that? Because I can imagine if you perturb it too much in your tau example, where you take whether it's a bi or a cell case, if you perturb the point of importance by a lot, it does change the output. But if you perturb it by a very small amount, it probably will not change the output. So you might miscalculate it as a not important feature if your perturbation is not strong enough. So how would you account for that?
So I think that this has to do, this is probably domain specific. So I don't think that I have a very general answer for this. I think that you have to play with different perturbation operators, and you see that some, maybe your output might be sensible to some and not to the others. So that's why I kept the formalism very generic, because I don't want to claim that one perturbation operator is always better than the others. Sometimes, I use this Gaussian kernel perturbation operator that I kind of hinted. Sometimes I use the moving average. And actually, I have an experiment in the supplementary material where I kind of compare if the mask outputted by these different perturbation operators are the same.
Oh,
and
interesting.
you can show that in some settings they're actually really similar. But I guess that I didn't explore it enough to actually know if there is this will always be the same. Like I didn't see a difference where there was a big qualitative difference between two perturbation operators, but I guess it could exist in practice. So
awesome. Okay, thank you. Are there more questions from folks? Okay, maybe then if not, we can thank Jonathan again, and we'll put up the recording on our YouTube channel by tonight. And if you have follow-up questions, you can reach out to Jonathan, or we also have a form on our website where you can post your follow-up questions. So thanks again, Jonathan, and hope to see everyone next week.
thank you very much.
Thanks, Jonathan.
Thank you.